Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is resonance. Sorry about that. There we are. Topic is resonance. A couple of the questions we're going to be answering today are: what is resonance? What do we mean by the term natural frequency when we're talking about an object? And also, how can we explain resonance using some wave terminology? So in other words, what does resonance have to do with waves? So just to show you where we are in the homework schedule, it is lesson 6. The section is 6.2 in the textbook. Along with watching this video, it would be great if you could take some notes on the section and possibly also try some of the homework questions. There aren't too many questions in this section, and you'll be happy to know, maybe, that there's really not much math associated with the questions. These questions are more communication type questions where you have to explain something in words. So if you want a little bit of a break from the math, I think you'll enjoy this. There's a couple of videos to watch. I recently tried this first one, and I noticed that the video no longer existed. But if you just search under the following title, the Tacoma Narrows Bridge Collapse 1940, you'll find plenty of videos on the topic. And if I were you, I'd just watch the shortest one, or possibly the one that I'm going to show you a little bit of in this video. After class, you can try this question here, and let's get started. So first of all, I'd like you to think about these three objects here. They all have something in common. One is a swing set, which I'm sure you've all been on at one point or another. Another one is a guitar, which I'm sure you've all experienced either by listening or possibly by playing. And the other one is a wine glass, and I'm not so much focused on the wine in it, I'm focused more on the glass, just in case anyone's wondering. So what do these all have in common? Well, first of all, try to imagine being on the swing here. And you and your friend go to the park, and your friend starts giving you a push. In fact, let's change it up a little bit. Let's imagine that you and your little brother or sister go to the park. Now, your little brother or sister, being really young, could he or she push you and get you moving on the swing? Absolutely. You don't have to be strong to get someone going on a swing. You just have to be good at timing your pushes. And in fact, even your little brother or sister pushing just, lightly, but at the right time, can actually get you moving quite high. So think about that as we go on with this explanation or this analysis. But what I also want you to think about is the fact that when you get on a swing, it swings back and forth a certain number of times in a certain number of seconds, and this allows us to calculate what we call frequency. We've been doing it for the entire course so far. Here's an experiment to try. You go on the swing and let your little brother or sister push you and figure out what your frequency is using a stopwatch. Now reverse it. You push your little brother or sister. Put them on the exact same swing. And you might be surprised to find out that even though you're heavier and your little brother or sister is younger, and even though you push harder and your little brother or sister pushes lighter, your frequencies will actually be the same. In other words, if you don't believe me, try this. But what I'm trying to say is that the frequency of the swing only depends on one thing. It doesn't depend on who's sitting here and how heavy he or she is. Do you know what the frequency of a swing, or really a pendulum, depends on? I'll give you a moment to think about it. If you guessed that it's the length of the pendulum, you're correct. In fact, the only thing that really determines the frequency of a pendulum is the length. And so I'm going to draw that in here. Here's a line indicating the length of the pendulum or the swing, and that's the only thing that determines the frequency of a pendulum. If you want, take a string, hang something heavy on it, and swing it back and forth in your hand. Now measure the frequency with the stopwatch, and then repeat this experiment, but this time with a shorter string or a longer string, and you'll quickly see that this is what affects the frequency. Well, we call this the natural frequency of the pendulum or the swing. Natural because it's almost as if the swing wants to vibrate at a certain frequency, which is only dependent on its length. Now let's take a look at the guitar. If you have a guitar, go pick one up. If you don't, then try to remember a time you ever played one. If you pluck any of the strings, it doesn't matter how hard you pluck, you always get the same note, which is really the same frequency in physics language. In other words, the strings seem to have a frequency that they like to vibrate at. We call this, once again, their natural frequency. And finally, ask your parents before you do this, because I don't want to be responsible for you breaking expensive wine glasses, but go get a nice delicate wine glass And what you got to do, you can put some liquid in it or you don't have to, but just wet the tip of your finger with a little bit of water and run it around the outside of the wine glass. And as you do this, your finger will sort of vibrate as it sort of catches on the glass surface there. And these vibrations will get the wine glass vibrating. No matter how you move your finger around the rim, the wine glass will actually make a sound, much like a musical instrument. And again, the frequency is really only determined by the shape of the glass and the type of glass and how delicate it is and things like that. If you put liquid in, that will also affect the frequency. But once again, the wine glass seems to have a frequency that it likes to vibrate at. So once again, the term natural frequency. And that's really all natural frequency is. Every object has its own natural frequency, a frequency it likes to vibrate at. So now, where are we going with this? Well, I'd like you to take a look at this next slide and ponder this thought. If we can add energy at the natural frequency, we're going to get large amplitude vibrations. What do I mean by this? Well, let's go back to the example that I was discussing over here with the swing. Remember how I talked about how you could get your little brother or sister to push you quite high on a swing. He or she doesn't need to be strong. He or she needs to time the vibrations, the pushes, at the right moment. In other words, the frequency of pushing must match the natural frequency of the swing. If your little brother or sister can do that, you're going to go quite high in terms of your vibrations here. And by the way, how high, when we're talking about a swing, as you're swinging back and forth here, really is talking about the term amplitude. So there's another physics term that we want to bring into the discussion. We've already talked about frequency of pushes and natural frequency of objects. Now we're talking about the amplitude of the pushes that you're giving. Now we're talking about the amplitude of the vibrations of the object that's being pushed. Think of a guitar string here. In a guitar string, it likes to vibrate at a natural frequency, but have you ever noticed with this kind of guitar, this is an acoustic guitar, it does not need any sort of electronic amplification. They're quite loud even without electronic speakers or anything like that. Why is that? Well, as you're going to see later on, the way the guitar is designed is that the vibration of the strings, which happens at a certain natural frequency, actually is equal to one of the natural frequencies of the wooden sound box. This is called the sound box or the resonance box. Just write that in there. What's going on here? How is it that a tiny little string with no electronic amplification can make a guitar sound so loud? Because some of these guitar players, if you listen to them playing an acoustic guitar, they're quite loud. Well, very simply, the frequency of the string matches the natural frequency of the wooden box. And the wooden box is quite large, the sound box here. It begins vibrating. Can you see how this is kind of the same as your little brother or sister pushing you on the swing here and matching his or her frequency to the swing's natural frequency? The amplitude of your vibrations, your swings, is going to get quite large. Well, in sound, that means loud. And finally over here, if you do try this at home, you're going to notice that the wine glass rings quite loudly if you keep running your finger around the rim. And then you're going to see pretty much the same thing that's going on with the guitar here. What we're trying to do is to match what's sometimes called the driving frequency or the pushing frequency along with the natural frequency of the object. And if we can do this, we will see large amplitude vibrations. In the object. Okay. Now let's take a look at some examples of this happening where you don't have to sit and look at a picture, you can actually watch some videos. Some of the videos will be the ones that are in the homework schedule here. but a couple of them I also dug up for you. So let's just have a look now. We'll switch over to our good friend YouTube. Okay, here's one that's interesting. Now this is a physics video put on by someone else, and you see the credit is given. I haven't tried to hide this video's source. And so this guy here, watch what he's doing. I've muted the sound so that I can talk over it, but he's made a couple pendulums out of these chocolate Easter eggs, these cream eggs. And they're both the same length, so you know they have the same frequency. Now he gives one of them a push, and let's think about what this means. He's giving one a push, and therefore it's going to swing at its natural frequency. Now just go back a little bit to the beginning, or close to the beginning. You see that the tops of the two strings are connected via another string, which is on a retort stand. There you can see a little bit clearer. So when he swings one pendulum over here, the vibrations will be transmitted via that upper string into the other pendulum. And of course the other pendulum, having the same frequency as the first pendulum, because it has the same length, what's it going to do? It's going to start vibrating itself. Only something really weird happens here. One of them starts vibrating, the other one stops. It's as if they're trading vibrations. Do you see that? One of them stops, now it starts going, and the other one stops. And they take turns. It's really, really weird. You should definitely watch this video if you want to see, to hear what he has to say. But what did we notice there? We noticed something else about these vibrations. The idea that if you can match the driving or the pushing frequency with the natural frequency of another object, large amplitude vibrations will occur. Why will this occur? Well, I'll give you a little hint. Back in the video over here, when one moved a lot, the other moved very little. And when the other moved very little, when the other moved a lot, the original one moved very little. There's a sort of energy idea going on here. The idea that they can't both be vibrating at the maximum amplitude, because then you would have more energy than you started with. In the beginning, this experimenter or demonstrator, he only pushes one. So he gives the system some energy. When this one stops vibrating, it's because it's transferred its energy to this one. And now this one's going to stop. Where's the energy going to go? Back here. Do you hear sort of echoes of the law of conservation of energy? That energy can't be created or destroyed. It can only be transferred from one form to another, or possibly from one object to another. Well, that's what's going on here. So we go back and we change our analysis of, or we add to our analysis of resonance. We want to match the driving frequency with the natural frequency. This will result in large amplitude vibrations, because what we are doing is we are causing the transfer of energy into an object. And now I'd like you to step back and think about what we've talked about. We've talked about frequency, a wave phenomenon. We've talked about amplitude, also a wave phenomenon. We've talked about energy. Remember, energy is carried by waves. Waves are disturbances in a medium which transmit energy. So really, this is a wave phenomenon. We have a name for this, and we call it resonance. The transfer of energy from one object to another when those frequencies match, resulting in large amplitude vibrations of the object. Let me show you a couple of other videos here. This one, which is in your homework schedule, I'll let you watch it. But what we have here is a speaker which is going to produce sound at a very specific frequency. And here's our good friend, the wine glass. This is a little bit different than running your finger along the edge of the wine glass. What happens here, and you're going to see in the video, is the demonstrator over here, he's going to tune the frequency of the speaker so it matches the natural frequency of the glass. He's going to add energy at a specific frequency to the glass, and the glass will begin to vibrate. Now, because this is electronic and easily controlled, unlike, say, a human voice, he's going to add a lot of energy at the right frequency. The vibration of the glass will get to a point where it's actually going to shatter. So he's going to shatter this wine glass with sound waves. Check it out. It's in your homework schedule. And finally, no discussion of resonance would be complete if we didn't talk about this. the so-called Tacoma Narrows Bridge, a suspension bridge that was built in the northwest of the United States, the Pacific Northwest, in Tacoma, which is in Washington State. And they built it across what was called Puget Sound, or still is called Puget Sound. It's a body of water. It was one of the longest suspension bridges in the world at the time. And very soon after they built it, this is what it started doing. I'll play the video with the sound muted. The bridge actually swayed quite violently from side to side. I don't know if you've ever seen anything this crazy, but this actually happened. There's a picture of a car that got stranded on the bridge. And so they show now a picture of one of the spans or the wires that hold this thing in place, or they're supposed to hold the bridge in place. You see how it's shaking. Why did this happen and what resulted? Well, obviously there's a crash that's about to occur. The bridge is swaying, very large amplitude vibrations. Here from the waves in the water, you can see that the wind was quite high on that day. Does this look familiar to you? Does this kind of look like a lab we've done in class, the vibrations here? Hint, standing waves. So this is what the bridge ended up doing as a result of the wind, and very soon after, I think it collapsed. I think we're going to see the collapse very soon. The bridge was just not strong enough to take all of these forces that were tearing at it, and eventually it collapsed. I think that's coming up pretty soon. Hopefully pretty soon. There's a guy trying to get out of the way before I think he was the owner of the car, and I heard that his dog was in the car. He was trying to get the dog out. The dog didn't want to come out. The dog was too scared. Anyway, not long after, the bridge collapsed. Unfortunately, the dog died. Fortunately, that was the only loss of life. There it goes. Fell into Puget Sound. Not a happy ending. My question to you is, what was going on and how does this deal, or what does this have to do with resonance? Well, let's see if we had some of the ingredients of resonance. Did we have large amplitude vibrations? Absolutely. Were they at a certain frequency? Yeah, just watch that bridge vibrating and moving through its vibrations in a certain amount of time, you'll measure a frequency. Energy was certainly transferred to it. Nothing gets moving like that without picking up some energy. But the question is, what was driving the bridge? What supplied the frequency? The hint is that it was a very windy day. But wind doesn't blow at a certain frequency. Like you don't get wind that sort of pulses the way you push someone on a swing and pulses. What was going on? Well, I'll give you a little hint. Another video that I pulled up shows this. How many of you would like to have a Mercedes-Benz SLS AMG? I don't even know what that is. It just sounds expensive. Sure, I'd love to have one. But before they put these cars out on the road, they give them what are called wind tunnel tests. They put them in a wind tunnel to see how they'll behave in terms of the aerodynamics. I've got a little bit of sound on in the background. You can see the wheels are spinning on a treadmill basically. And as the wind blows over the car, they inject a little bit of smoke so they can watch the pattern and they can see just how aerodynamic the car is. Now what I want you to focus on is the back part of the car where the smooth wind stream is starting to break into bits. Now let's see where they show that in here. I think you'll start to see it right around here. Take a look right here, and you're going to see that as the wind goes over, it goes up, down, up, down, up, down. Now there's a spoiler part of the car. I don't want you to focus on that. I just want you to focus on just that up-down motion that you see happening there. Well, that same thing is what was happening to the bridge as the wind went over it. And believe it or not, the wind, just air, pushing at the bridge at a certain frequency, guess what? The frequency of that wind matched the natural frequency of the bridge. The amplitude of the bridge's vibrations increased until finally the bridge, the material it was made of, could not stand it anymore, and it was ripped apart. All right, folks, so that concludes our lesson. We've answered all the questions that we set out to answer. What is resonance? What do we mean by natural frequency? And how can we explain what's going on in resonance using wave terminology? Your task then is to think of some other examples of resonance that I have not mentioned. There are a few, and I'll do some demonstrations in class here. I'll show you the pendulums, the video that we watched with the Easter eggs. I'll show you that in class, and I'm also going to show you another example called matched tuning forks. But see if you can think of any other ones. All right, folks, thanks for watching, and have a nice day.